Welcome to Maths Academy Tube. In this video, you will get a variety of problems related with application of derivatives. I believe that if you watch the full contents of this video, you can grasp the whole concepts of the unit. So stay with me. The first problem is, which of the following is necessarily true about the function f? So we will identify a necessarily true statement about a certain function f. So let's check for A. The statement in A is if f is continuous at x is equals to a, then it is differentiable at x is equals to a. So this statement is false. For example, if we take a certain function f of x is equals to absolute value of x, this function is continuous. It's continuous at x is equals to 0. Obviously, this is continuous at x is equals to 0, as you can check. But this is not. But it is not differentiable. It is not differentiable at x is equals to 0. But it is not differentiable at x is equals to 0. Or you can check that the derivative of this function, the derivative of the function absolute value of x is x over absolute value of x. So this is not defined at x is equals to 0. Therefore, it's not differentiable at x is equals to 0. So A is not necessarily true. Let's check for B. If we see the statement in B, if f is not differentiable at x is equals to a, then the right hand side limit and the left hand side limits are different. So we need to carefully examine the statement in B. The statement in B is equivalent to the statement in A. Using the logic concept, we know that P implies Q is equivalent to its contrapositive. The negation of Q implies P. These two compound propositions are equivalent. So the statement in B is the contrapositive of the statement in A. They are equivalent statements. So B is not true. Let's check for C. In C, if f is differentiable at x is equals to a, then the right hand side limit and the left hand side limits are the same. Therefore, this is always true statement. Any differentiable function at x is equals to a is continuous. Okay, this condition is the condition for continuity. So f is differentiable at a certain number at x is equals to a implies the function is continuous. You can get the proof of this statement. We can prove it, but for now, just keep in your mind that every differentiable function is continuous. So it is true. It is always true. So we need to check that D is false. For example, the statement in D, if the derivative of the function at a is 0, then f attains its maximum at x is equals to a. This is not necessarily true. For example, if we take a certain function, a constant function, say f of x is equals to some number m, obviously its derivative is 0 for all x, right? So the function f derivative at a is 0 doesn't mean that the given function attains the maximum value at some number. So this is not always true. Therefore, our answer for this statement is C. At what values of x does the given function here have local maximum? Here we use second derivative test to determine the value in which the function will have local maximum or local minimum. If the second derivative of the function at some critical number c is less than 0 or negative, then at x is equals to c, the function will have local maximum, right? So this is the condition for the local maximum. Therefore, we have the function. The function is f of x is equals to 1/3 of x cubed minus half of x squared minus 2x plus 1. This is our function. So we need to know its second derivative. So let us proceed. The first derivative of this function is take the exponent. It's very easy. Take the exponent and multiply with its coefficient. Then the first derivative becomes x squared. Okay, here you will make it minus 1. Minus, again, we multiply this exponent with its coefficient, then it becomes x. Here you subtract 1 from the exponent, then minus 2. This is the first derivative. For this given function, its first derivative is this one, and the second derivative can be obtained from the first derivative. Then the second derivative is 2x minus 1. This is the second derivative, okay? So we have the second derivative, and we need to know also the critical numbers, okay? The critical numbers can be calculated by solving the first derivative for 0. So let us calculate the critical numbers. Critical numbers here, they will be obtained by solving first derivative for 0. So our first derivative is this one, x squared minus x minus 2. So x squared minus x minus 2 is equals to 0 will give us the critical number. So here you can use a quadratic formula to calculate this equation, but for me to save the time, I use factorization. X squared minus x minus 2 can be written as x minus 2 times x plus 1 is equals to 0. So this implies x minus 2 is equals to 0 or x plus 1 is equals to 0. So x is equals to 2 or x is equals to minus 1. These are the critical numbers, okay? These are the critical numbers. So we substitute these critical numbers in the second derivative. So the second derivative is f of f double prime is 2x minus 1. So substitute one of the critical number here. The second derivative at 2 is 3, you can check, which is a positive number. So at 2 we can't get the local maximum. Again, let's calculate the second derivative at minus 1, the other critical point, number. So the second derivative at minus 1 is 2 times minus 1, which is minus 3. This is a negative number. Therefore at x is equals to minus 1, we get the local maximum. Okay, we can get the local maximum. So our answer will be B. On which of the following intervals is the graph of f of x is equals to ln of x squared plus 1 is concave up? Here we need to know the condition for concavities. The function will be concave up in the interval where the second derivative is greater than or equals to 0. In this case, the graph will be concave up, Otherwise, if the second derivative is less than or equals to 0, the graph will be concave down. In this interval, it becomes concave down. So we evaluate the second derivative to be positive, so that we can determine the interval in which the function becomes concave up. So let us find first the derivative of this function. Our function is f of x is equals to ln of x squared plus 1. So the derivative of this function will be ln derivative means the inner derivative over x squared plus 1. So this becomes 2x over x squared plus 1. This is the first derivative. So we can calculate the second derivative from the first derivative. So the derivative of 2x over x squared plus 1 will give us the second derivative. So this derivative means applying derivative for quotient, 2x derivative times x squared plus 1 minus 2x times x squared plus 1 derivative over x squared plus 1 the whole square. So this is the same as 2 into x squared plus 1 minus 2x times 2x, because x squared plus 1 derivative is 2x, over x squared plus 1 the whole square. Therefore, the second derivative for the given function is minus 2x squared plus 2 over x squared plus 1 the whole square. Okay, you can simplify this one so that it gives us this expression. Now, to find the interval of concavity, particularly the interval in which it becomes concave up, we evaluate the second derivative of the function for greater than or equals to 0. This implies minus 2x squared plus 2 over x squared plus 1 the whole square is greater than or equals to 0. Here this expression is always positive. Therefore, the given inequality will be solved by this one, minus 2x squared plus 2 is greater than or equals to 0. Okay, so this can be written as minus 2 into x squared minus 1 greater than or equals to 0. So this can be written as x squared minus 1 less than or equals to 0. Dividing both sides by negative will reverse the inequality. So this inequality is true for x between minus 1 and 1. Okay, you can use sign chart, or for me I prefer to use line chart. Take the zeros of this expression, which are minus 1 and 1, and the leading coefficient is positive. Therefore, I start from positive, negative, positive, right to left. So this expression is negative in between minus 1 and 1. So in this interval, the graph of the given function is concave up. Therefore, our answer is D. Water is poured into a cylindrical tanker of radius 5 meters, and the rate of the volume of water also changes with 10 meters cubed per minute. What is the rate of change of the height of the level of water when it rises to 3 meters? Here we are asked the rate of change of the water level when the volume of the water is changing with time. So to calculate the rate of change of the level of water, we need to know first the volume of the cylinder, which is base area, which is circular, pi r square times h. This is the formula for the volume of the cylinder. Here we are observing that the water is poured into the cylindrical tanker of radius 5 meter with this rate 10 meter cube per minute. Okay, that means the rate of change of the volume is given as 10 meter cube per minute, and the radius of this cylindrical tanker is 5 meter. Then we are asked the rate of change of the height of the level of water when it rises to 3 meters. So V is equals to pi r square times H implies dV by dt. Taking the derivative both sides with respect to t will give us d by dt of pi r square H. Now pi is constant, r is also constant with respect to the change in water level. So this becomes pi r square dh by dt. The required thing is dh by dt, right? So the given thing is here 10 meter cube for the rate of change of the volume of water and 5 meter for the radius. So we have all this thing. dV by dt is 10 meter cube per minute. Pi times r square is 5 meter square times dh by dt. Now this gives us 10 meter cube per minute is equals to 25 pi meter square times dh by dt. Now dividing both sides by 25 pi meter square, 25 pi meter square will give us dh by dt, or the rate of change of the height of the water level, which is 10 over 25 meter per minute. Or simplifying this will give us, there is pi also here. So simplifying this will give us 2 over 5 pi meter per minute will be the rate of change of the height of the water. So the answer will be B. On which of the following interval does this function increases? So there is a condition for monotonicity, meaning that the interval in which the function is increasing or decreasing. So f is increasing if if this condition is satisfied. The first derivative is greater than or equals to 0. So this is the condition for increasing. Then it becomes decreasing. F is decreasing if the first derivative is less than or equals to 0. This is the condition for monotonicity, increasing or decreasing. So our function is f of x is equals to x to the power of 4 plus 4x. This is our function. So we need to calculate its first derivative. So its first derivative is 4x cubed plus 4. So solving this for greater than or equals to will give us the interval in which the function is increasing. So f is increasing if 4x cubed plus 4 is greater than or equals to 0. Or this implies 4 into x cubed plus 1 is greater than or equals to 0. So dividing both sides by 4, we get x cubed plus 1 is greater than or equals to 0. Here we need to be very technical. We know that a cubed plus b cubed is equivalent to a plus b times a square minus ab plus b square. This is, you need to be very familiar with factorization of cubic expression. Therefore, using this concept, we can factorize x cubed plus 1 as x plus 1 into x squared minus x plus 1 greater than or equals to 0. You can check that the product of these two expressions will give us x cubed plus 1. So this expression is always positive, as you can check. Therefore, the product of these two things are positive whenever x plus 1 is positive or greater than 0. So this implies x is greater than or equals to minus 1, or you can use the interval notation. Minus 1 up to infinity is the interval in which the function f is increasing. So the answer for this is B. At which values of x does this function have a local maximum? As I have told you in question number 3 or 2, you can check it back, but we can get local maximum at a certain critical number, in which that critical number, the second derivative of that critical number is less than 0. So this is the condition for the local maximum. Okay, you need to calculate the critical number, where this C is critical number. Okay, so we need to calculate the critical number, and that critical number will give this condition to say that the given number gives a local maximum. So let's proceed to calculate first the critical number. So the function f is 1/4 of x to the power of 4 minus 2x squared. This is our function. So to calculate the critical number, we use the first derivative. So the first derivative of this function is x cubed minus 4x. Okay, this is our first derivative. So solving the first derivative for 0 will give us a critical number. So solving x cubed minus 4x for 0 will give us the critical number. So this means x into x squared minus 4 is equals to 0. This implies x is equals to 0, or x squared minus 4 is equals to 0. So we have three possibilities. X can be 0, or x can be 2, or x can be minus 2. There are three critical numbers in which the first derivative becomes 0. So let us take these critical numbers. But before taking the critical numbers, let's calculate the second derivative of the function. Our first derivative is x cubed minus 4x. Therefore, the second derivative is 3x squared minus 4. This is the second derivative. Now let us calculate the second derivative at the critical numbers. The second derivative at 0 is negative 4. Okay, you can substitute here the zeros here. So this is negative. The second derivative at 0 is negative. 0 will give us local maximum. Okay, again, let's check for the second derivative at 2. The second derivative at 2, again, substitute it here. The second derivative at 2 is 8. The second derivative at minus 2 is also 8. So both are positive. This is positive. This is both positive. So the only number that satisfies this condition, the second derivative at a certain critical number, is negative at x is equals to 0. Therefore, x is equals to 0 is the critical number that gives us the local maximum. Therefore, our answer is B. The volume V of a melting ice cube after T second is given by this one. How fast is the volume changing when T is 40 seconds? So the volume of a certain ice is given. V of T is 2000 minus T plus 0.T square. So we are asking the rate of change of this volume at T is equals to 4T. So let's calculate dV by dt, or the rate of change of the volume of this ice. So the derivative with respect to T will give us -1 plus 0.4T. So the rate of change of the volume of this ice at T is equals to 4T means -1 plus 0.4 times 4T. You can substitute in place of T. So this becomes -1 plus 60. So this is 15. Okay, so the answer for this problem is 15. A box is seen below is to have a square base and open on the top. It's open on the top, the base is square, and the volume of this object is 32 cubic units. The volume is given, which is 32 cubic units. Okay, if x length of each side of its base and y is its height, how many units should x and y be in order to make the box with the smallest amount of material? The box is made up of the whole body part, which is the total surface area of the box. The total surface area means the lateral surface area plus the area of the base. Since it is open on the top, we calculate only the area of the base. But the lateral surface area of this box, it has 4 faces, therefore the lateral surface area is 4xy, and the base area is x times x, which is x squared, because the base is square. So this amount is required to make this cubic object. So we are asking the smallest amount of material to make this cubic object. We know that the volume of this object is base area, which is x squared times the height. So this is 32. Okay, this is 32. The other thing is the total surface area of this object is 4xy plus x squared. Now, to make it short, let me write this as A. Okay, call it simply A to mention A total. So from the given information in the volume, x squared times y is equals to 32 implies y is 32 over x squared. Okay, so here we substitute in A, area is equals to 4x times y, which is 32 over x squared, plus x squared. Therefore, we can completely determine A as a function of x, which is this one, which means 128 over x plus x squared. So we are going to find the smallest amount of material, the dimension for the base and the height. So let us calculate the derivative of this function to calculate the critical numbers. The derivative of this function is minus 128 over x squared plus 2x. Okay. The critical numbers can be obtained by solving the first derivative for the row or finding the value in which the first derivative becomes undefined. So let's calculate a prime for 0. This gives us minus 128 over x squared plus 2x is equals to 0. So this implies 2x is equals to 128 over x squared. This means 2x cubed is equals to 128, meaning that x cubed becomes, dividing both sides by 2, x cubed becomes 64. This means x is 4. The cube of some number is 64 when that number is 4. X is 4 means you can substitute here to calculate the value of y. You can substitute here y is 32 over x squared. So 32 over x squared means 4 squared. This is 32 over 16. The result is 2. The value of y is 2. Okay, the value of y is 2 and the value of x is 4. So our answer will be A. This gives us the minimum amount of material to make this box. Which one of the following is the set of all critical numbers of this function? As I have told you before, the critical numbers can be calculated by solving the first derivative for 0. So the function is 1/3 of x cubed minus the absolute value of 4x minus 1. Okay, this is our function. So its derivative becomes x squared minus 4x minus 1 over the absolute value of 4x minus 1. Now the first derivative is equals to 0, or the first derivative of this function doesn't exist will give us the critical number. Shortly, the critical numbers can be calculated at the point in which the first derivative is 0, or at the point in which its derivative doesn't exist. Obviously, the first derivative of our function is x squared minus 4x minus 1 over absolute value of 4x minus 1. So this function doesn't exist. The function doesn't exist at x is equals to 1 over 4, because it is undefined at x is equals to 1 over 4. Therefore, x is equals to 1 over 4 is one of the critical number. The other thing is the first derivative of this function becomes 0 whenever x squared minus 4x minus 1 over absolute value of 4x minus 1 is 0. So this function becomes this way. Okay, this function can be expressed as x squared minus 1 is equals to 0 for 4x minus 1 is positive number, or it becomes x squared plus 1 is equals to 0 for absolute value of x, for 4x minus 1 is less than 0. So we calculate this one for 0, but this cannot be, x squared plus 1 cannot be 0, but we can calculate the x squared minus 1 for 0. So this gives us x is equals to plus or minus 1. So there are three results: x is equals to 1 over 4 and x is equals to plus or minus 1. So the critical numbers are minus 1, 1 over 4, and 1. These are the critical numbers. So our answer is B. Suppose equal squares are cut from each of the four corners of a square cardboard whose sides are 72 centimeters long. here on the figure below, you can see a square cardboard whose length is assumed to be 72 centimeter. Okay, given this square cardboard, we want to produce a box from this square cardboard. So the resulting flaps are then folded up to form a box without a top. So we are going to cut some pieces, square pieces from the corner, from each corner of this cardboard to produce a box with which is open at the top. So the question is, what should be the length of the pieces that we are going to cut from each corner? Say the length is x, x by x, x by x, okay, from each corner, and we fold it up. Then the resulting base, the base of this box will be, let me use different color. This section, this part will be the base of the resulting, the base of a box. Okay, so if we cut x unit from each corner, this result is 72 minus 2x. Okay, the same thing, each of these things are the same. Okay, so the question is, what should be the size or the length of x to have a maximum volume for the box? So the volume for a box is given by base area times h. The base area for this case is 72 by 72, which is 72 minus 2x, the whole square, times its height, which is x. So now we have the volume as a function of x, which is 72 minus 2x, the whole square, times x. So to calculate the value of x in which the volume becomes maximum, we use the derivative of a function. Derivative of the volume should be 0. But first of all, what is the derivative of the given function? V derivative means the derivative of 72 minus 2x, the whole square, times x. You can apply product rule for derivative, so that applying product rule for derivative will give us this much, 72 minus 2x times 72 minus 6x. This is the derivative of the function. So solving this for 0, v prime for 0 will give us 72 minus 2x is equals to 0, or 72 minus 2x is equals to 0. So from this we can get x is equals to 36 or x is equals to 12. We can't use x is equals to 36, or we have to discard this value, because if you use this 36, 72 minus 2 times 36 is 0, which is meaningless. So we take x is equals to 12, so that you will have a maximum volume for the box when you cut 12 centimeter by 12 centimeter from each corner. Therefore, the answer is 12 centimeter. What is the absolute maximum value of the given function? We determine the absolute maximum or the absolute minimum at the critical number at the endpoints of the interval. The function f is given as 2x squared minus x to the power of 4 minus 4. This function is defined on the interval from 0 to 2. So the absolute maximum will be either at the critical number or at the endpoints. So let us evaluate each of these things. So the first derivative of this function is 4x minus 4x cubed. Okay, solving the first derivative for 0, we get 4x minus 4x cubed is equals to 0. This implies 4x into 1 minus x squared is equals to 0. So this becomes x is 0 or x is plus or minus 1. We have three critical numbers. So the critical numbers are minus 1. They are minus 1, 0, and 1. We evaluate the function at the critical number and at the endpoints. So let's see what the values of the second derivative looks like at the critical number. First of all, the second derivative is 4 minus 12x squared. So the second derivative at minus 1 and at 1 are the same, which is negative 8. Okay, so we expect the maximum or the absolute maximum at this number or at the endpoints, while we discard the 0, because the second derivative at 0 is 4, which is positive. We don't expect the absolute maximum at 0. Therefore, we expect at minus 1, 1, or at the endpoints. Now let us calculate each of these things on the function. F of minus 1 is 2 times minus 1 square minus 1 to the power of 4 minus 4. This result is 2 minus 1 is 1. 1 minus 4 is minus 3. Okay, this is minus 3. Again, calculate f of 1, which is 2 times 1 square minus 1 to the power of 4 minus 4. Again, the same number, minus 3. Okay. We have to also calculate the values of the function at the endpoints. The endpoints are 0 and 2. So evaluate the function at the endpoints. So substitute 0, it becomes 2 times 0 square minus 0 to the power of 4 minus 4, which is minus 4. And substitute 2, which is 2 times 2 to the power of 4, 2 square minus 2 to the power of 4 minus 4. So this is 4. 4 times 2 is 8. 8 minus 16 is minus 8. This is minus 20. So when we compare all this number, okay, the function will have an absolute maximum at minus 3. Okay, the absolute maximum value of this function is minus 3. So this is the absolute maximum. You cannot have any values for this function more than 3. So the answer is A. Which one of the following is necessarily true? If let's see each of them separately. For A case, if f derivative is 0 for all x in the interval, then the function is 0. This is not always true. For example, if we take f of x is equal to some constant number, which is different from 0, its derivative is 0 for any number x. Okay, so it cannot be a true statement. Let's check for B. If f of x is x squared sine x plus 5, then there is C in some interval 0 to pi such that its derivative at C is 0. Let's check. f of x is x squared sine x, then its derivative is x squared cos x plus 2x sine x. Okay, now its derivative at c is equals to 0 implies that c squared cos c plus 2c sine c is equals to 0. Okay, this means c into cos c plus 2 times sine c is equals to 0. So here c can be 0, or cos c plus 2 times sine c is 0. This expression implies tan c is equals to minus, here we have c, sorry, here we have c, so here we have c. So tan c is equals to minus c over 2. This will have a solution in this interval. Okay, so B is a true statement. We can check that the rest are not necessarily true. For C case, f of x is e the power of x plus x squared. Then this function is increasing throughout the real number. If this is true, if this is a must true, the first derivative should be always positive. So let's calculate the first derivative for this. It becomes e the power of x plus 2x. This is not always positive. For example, if you take x is equals to minus 2, this expression becomes negative. So C cannot be a must true or necessarily true statement. Let's check for D. If the derivative of the function at C is 0, then f attains its extreme value at x is equals to c. This is not always true. For example, if of x is equals to 10, its derivative is 0. That means f derivative at some number is also 0. So, but this function will not attain its maximum at a certain number c, because it is a constant function. Therefore, this is not necessarily true. So our answer is B. Let f be twice differentiable function on R. Which of the following is necessarily true? If f derivative at c is 0 at some real number R, then f has relative extreme value at x is equals to c. This do not works for a constant function. Therefore, this is not true. This statement fails whenever f is a constant function. Let's check for B. If f derivative is increasing, okay, if f derivative is increasing, if it is increasing, the second derivative should be greater than 0, because f is increasing implies its first derivative is greater than 0. So f prime is increasing means its derivative or the f double prime is greater than 0. So f double prime is greater than 0 is a condition for concave up for a function f. Therefore, this is necessarily true. Let's check for the rest. If f prime is 0 for all x, then f of x is 0. This is not always true. F of x can also be some number 4. It can be 4. The derivative is 0 for any x. So C is not true. F of x is increasing. If f of x is increasing, this holds. This is not true. If f is increasing, its first derivative is greater than or equals to 0. Therefore, the answer is B. A closed cylindrical can is to be made to hold 1000 centimeter cube of oil what are the dimensions that will minimize the total surface area of the can. Here, suppose we are interested to prepare a can with volume 1000 centimeter cube. So when we prepare the cylinder that can hold 1000 centimeter cube, what will be the dimensions R and H that gives the minimum total surface area? So here we need to know two things. One thing, the volume of a cylinder should be known. This is pi r square H. This is the formula for the volume of a cylinder. The other thing is the total surface area of a cylinder should be known. This is 2 pi r H, the lateral surface area, plus 2 times the area of the basis, pi r square H. So we have these two things. So having this thing, we will determine the dimensions that gives minimum total surface area. So the volume is 1000. Okay, we are planning to prepare a can that can hold 1000 centimeter cube, which is equals to pi r square H. So from this, dividing both sides by pi r square, H becomes 1000 over pi r square. So this is our H. Okay, this is the H value in terms of the radius. So now we can calculate the total surface area in terms of R, which is 2 pi r into H, which is 1000 over pi r square, plus 2 pi r square. Okay, so now we can express the total surface area as a function of R. Here, pi by pi and r by r, it gives us 2000 over r plus 2 pi r squared. This is the area, the total surface area in terms of r. So to get the dimensions, we have to calculate the critical numbers. So we calculate the critical numbers by solving the derivative of a for 0. That means the derivative of a means minus 2000 over r squared plus 4 pi r is equals to 0. If you want to know how this comes, you can visit my videos on derivatives. I did a lot of problems on derivatives. So for now, a derivative is equals to 0 implies this one. So solving for r, it gives us 4 pi r is equals to 2000 over r squared. So this becomes 4 pi r cube is equals to 2000. Now dividing both sides by 4 pi, r cube becomes 500 over pi, or r becomes cubed root of 500 over pi. Okay, you can guess that the answer for this problem is D, but we have to clearly define H, or we have to calculate H. Actually, H is here. H is 1000 over pi r squared. So we have r here, substitute here r, then we can get 2 into cubed root of 500 over pi. Okay, so the dimension of this cylinder that can give the minimum total surface area is here in D. The graph of y is equals to 5x to the power of 4 minus x to the power of 5 has a point of inflection at some point. So here we evaluate inflection point at the second derivative, right? So the function is y, or say y is our f of x, which is 5x to the power of 4 minus x to the power of 5. So the inflection point can be calculated. Inflection point can be calculated by solving the second derivative for 0. Okay, solving the first derivative for 0 will give us critical point. Solving the second derivative for 0 will give us inflection point. So we calculate the second derivative. So f derivative is 20x cubed minus 5x to the power of 4. This is our first derivative. So the second derivative is 60x squared minus 20x cubed. This is our second derivative. Now to get the inflection point, we solve the second derivative for 0. Our second derivative is 60x squared minus 20x cubed is equals to 0. Let us factor out something in common. 20x squared into 3 minus x is equals to 0. This implies x is equals to 0 or x is equals to 3. So this becomes 0 whenever x is 0 or x is 3. So at x is equals to here, at x is equals to 0, look, our function is 5x to the power of 4 minus x to the power of 5. So whenever x is 0, the function becomes 5 times 0 to the power of 4 minus 0 to the power of 5, which is 0. Therefore, one of the inflection point is 0, 0. The other inflection point is at 3. Okay, f of 3 is 5 times 3 to the power of 4 minus 3 to the power of 5. 3 to the power of 4 is 81. 81 times 5, this is 5 times 81 minus this is 243. Okay, so their difference is 405 minus 243, which is 162. So the other inflection point is 3,162. So these two are the inflection point. So our answer is D. Which of the following is a set of critical numbers for this function? So as I have told you before in one of the questions that I did before, the critical number for any function can be obtained by solving the derivative of the function for 0 or finding the point in which the derivative doesn't exist. So let us do it. The first thing, the derivative of this function is 4x squared plus x over absolute value of x. Now we solve the first derivative of this function for 0, or we find the point in which f derivative doesn't exist. Now the derivative becomes 4x squared minus 1 if x is negative. It doesn't exist. The first derivative doesn't exist if x is 0, or the first derivative becomes 4x squared plus 1 if x is positive. So we can explicitly describe this function in these three pieces. So definitely x is equals to 0 is one of the critical number, because the first derivative the first derivative doesn't exist at x is equals to 0. Therefore, x is equals to 0 is one of the critical number. The other critical number is, this is a critical number. The other critical number is a number in which the first derivative becomes 0. So we solve 4x squared. Okay, 4x squared minus 1 for 0. This implies x becomes x squared becomes 1 over 4, which means x is equals to plus or minus 1 over 2. So we do have another two critical points numbers here. We have x is equals to 0. So the other is 4x squared plus 1. We can't have a solution for this one. Solving for 0, this will not have a solution. So the critical numbers are minus 1 over 2, 0, and 1 over 2. These are the critical numbers for the given function. Therefore, our answer is D. Air is being pumped into a spherical balloon so that its volume increases at 50 centimeter per second. Okay, there is a spherical balloon. Okay, air is pumped into this spherical balloon at the rate 50 centimeter per second. That means the rate of change of the volume through time is 50 centimeter cube per second is the rate in which the volume is changed. So how fast is the radius of the balloon increasing when the diameter is 5 centimeter? Here the question is the rate of change of the radius. Okay, so this is the question. So basically the volume of a spherical object is given by the formula 4 over 3 pi r cube. Okay, so when we take the derivative both sides with respect to t, it becomes d by dt of 4 pi r cube, which is 4 over 3 pi r cube, which is given by 4 pi r square dr by dt. So our dv by dt, or the rate of change of the volume with time, is given by 4 pi r square times dr by dt. Now we have everything here. dv by dt is 50 centimeter cube per second, okay, which is equals to 4 pi times the radius of this spherical balloon is 5 over 2, because the diameter is 5. So the radius is 5 over 2 and square it, then dr by dt. Then this becomes 50 centimeter cube per second is equals to 4 pi times 25 centimeter square over 4 times dr by dt. Now this can be cancelled out. So dividing both sides by 25 pi, it becomes 2 over pi centimeter per second. So the rate of change of the radius with time will be 2 over pi centimeter per second.